All right, so we're going to do another volume problem. This time it says we're looking for the volume of the solid generated by revolving the region bounded by y equals 4x minus x squared and y equals x about the y-axis. Okay, so notice for this guy right here, we're going to do kind of what we've been doing whenever we are working with a quadratic function. I'm going to factor this. It just factors to x times 4 minus x. Now my reason for doing that is if I'm going to sketch this out, and you'll notice again I'm only using the first quadrant of the xy plane, not because it's always going to happen for every problem that we work on in this section, but just because the examples that I've done, all of the regions have lived in the first quadrant. But anyways, this is a quadratic with a negative leading coefficient. That tells me, oh, and it's in x, it's not in y. That tells me that it's going to be a parabola that opens downward. And if I know what the x-intercepts are for that parabola, that helps me graph it. By factoring into this form, if I plugged a 0 in for y, I can see that my x-intercepts would be 0 and 4. So 0 and 4. My parabola is going to look something like this, okay? Next, I'm going to sketch the line y equals x. That's the other curve. And that's going to end up looking something like this, okay? Here is the region that I want to revolve or rotate about the y-axis. So it's going to do something like that, okay? Let's draw a little rectangle here. So here's like my approximating rectangle. Notice that I drew it so it was parallel to the y-axis so that it'll kind of rotate around like this and create a cylindrical shell. And let's identify the position of this rectangle as x, because notice it would be going down to the x-axis here. So right away I can see that I'm going to have to integrate with respect to x, okay? But in order to do that, the integral is going to have limits of integration. So what are my limits of integration? Well, I would have to figure out the interval on the x-axis that this region is defined over. I can see pretty easily that it goes from 0 to something. What is that something? Well, it's going to be the x value of the point of intersection of these two curves. So I can solve for that by setting these two expressions in terms of x equal to each other. I can say 4x minus x squared, which is one of my curves, equals y equals x. So I'm just plugging the x in there. And I'd like to solve this, okay? So let me subtract that x over here to give me 3x minus x squared equals 0. Factor an x out, which gives me x times 3 minus x equals 0. This gives me two solutions, x equals 0, which we already knew is one of our solutions, and x equals 3, which I can see is this value right here. Okay, x equals 3. Okay. So the next thing I'm going to want to do is figure out exactly how to set up my integral using the image that I have here. And again, I do want to point one thing out. You really need to accept the fact that my graphs and my images are going to be way off scale. They're not going to be super accurate. Like I keep saying, you really just need to have the relevant information here. So the scale of this is way off. If 4 is over here, this would not be 3, right? Hopefully you can see that. Like 3 should be much closer to 4 than it is in my drawing, and that's okay. We're just going to try to imagine that as being correct. But with that said, let's go ahead and see if we can find the volume of this thing. So first of all, we're rotating about the y-axis. I want to know what the distance between my rectangle and that axis of rotation is, because that's going to become the radius, and that would simply be x. That's this distance right here. What is the height of this rectangle, though? Well, this time the rectangle doesn't go all the way down to a coordinate axis. It's bounded above by a curve and below by a different curve. So kind of like we did with the washer method, I can get the height of this rectangle by taking my expression that represents my upper curve, my higher curve, and subtracting the expression that represents the lower curve. That would be 4x minus x squared minus x. So 4x minus x squared minus x, which I can simplify. That becomes 3x minus x squared, like that. Okay? That thing is going to represent the height of that cylindrical shell. So when I set up this integral here, my volume is going to be the integral from 0 to 3. And then I have the circumference, which is 2 pi r, my radius, in this case, which is x, times the height of my rectangle, which here we determined to be 3x minus x squared, times my thickness, which is always either a dx or a dy. dx in this case, because that's what the variable is in these functions. Okay, so next step, I can simplify things a tad if I factor a 2 pi out. Distribute that x in. It's not a constant, so it can't come out, but it can be multiplied into here to give me 3x squared minus x cubed. Okay, and I have a dx here. That's a nice simple polynomial, so now I'm going to end up with a 2 pi times x cubed minus x to the 4th over 4, and we're going from 0 to 3. I can see pretty clearly here that if I plug a 0 in, this 0 in for these x's, I get a 0, which contributes nothing, so I'm just going to be plugging my 3 in here. I have 2 pi times 3 cubed, which is 27, minus 3 to the 4th power, which is 81 over 4. And I'm looking at my notes. I realize I actually didn't work this one out all the way, so I actually do need to do the arithmetic for this. Let me multiply that 2 in, because I want to bring that denominator down a little bit. That's going to be 2 times 27, which is 54, minus 81 halves. That makes things a tad simpler. Let's get a common denominator here. 54 times 2 is 108. 108 minus 81 over 2. What is that? That would be 27 halves. So this is going to be 27 pi over 2 when I bring that pi in as well. Let me just double check, make sure I did that correctly. Yeah, that's right, 27 pi over 2. Okay, so that's our answer. And you can see what was different about this problem was that the height was not determined by just one function, but by 2 of them. And I had to subtract the upper minus the lower to get the height of that rectangle. Okay? So that's one way in which these problems can be a tad more complicated than the previous examples that we saw. Let's do another example. This time we want to find the volume of the solid generated by revolving the region bounded by y equals the square root of x and the line x equals 2y about the line x equals 5. Okay? This is different in the sense that we're revolving a region about a line that is neither the x nor the y axis. We saw examples like this in the previous section, but this is our first time encountering one of these with the shell method. So let's start by sketching our region. Again, I only need the first quadrant for this one, specifically because y equals the square root of x only lives in the first quadrant anyways. So that's y equals the square root of x right there. X equals 2y. That's a line, and you can either think of it as x equals 2y, or you can think of it as y equals 1/2 x if you wish. That's going to be a line with a slope of 1/2 passing through the origin, and it's going to look something like that. Okay, so that is that line right there, and I can see the region that we have bounded here. Okay, so I need to find the volume of the solid obtained by revolving this little sliver of a region about the line x equals 5. Before we do that, let's figure out, well, first of all, the line x equals 5 is a vertical line. And so when I draw my approximating rectangles, I want them to also be vertical, like this. Okay, so that means I'm going to identify the position of this thing as an x value. And I need to know the interval on the x-axis over which I'm going to be integrating this thing. I'm smudging my graph down here. So in order to do that, I need to figure out what this right edge is here. I need to find this point of intersection and use its x value as the upper bound on this interval down here. So as before, I do that by setting things equal to each other. I have the square root of x as one of my functions and 1/2 x as the other function. Set those equal to each other. Square both sides to eliminate the radical. So I get x equals 1/4 x squared. I can subtract x from both sides. And then I would have a common factor of x that I can also factor out. So I'm going to get 0 equals x times 1/4 x minus 1. Hopefully you can see that that is what this thing would factor to once I move everything over. Okay, so what are the solutions to this? X can either equal 0 or it can equal 4. So 0 gives me the left endpoint here, 4 gives me the right endpoint. And we're revolving this thing around the line x equals 5. So this is the line x equals 5 right there. Okay? So hopefully now you can kind of see where our setup is going. Remember, what we need in our definite integral is a few things. We need our limits of integration, which is this interval right here, the interval from 0 to 4. Then I need circumference. So how do I find my circumference? Well, first, I'm going to need to know the radius of the cylindrical shell. Now, remember, we're taking this little approximating rectangle and we're rotating it not around the y-axis, but around the line x equals 5. It's going to go like this, right? So I need to know the distance from that rectangle to this line now, not to the y-axis. And that's what makes this a tad more difficult. How do we find this exact distance right here? Well, I know that the distance from the origin to here is 5, and I know that the distance from the origin to my rectangle is x. So if I only want this distance, I could take the larger distance, subtract the smaller distance, and that leaves me with this, 5 minus x. So the distance, or the radius of my cylindrical shell, is going to be 5 minus x. Hopefully you can see how we had to reason that out before we could put things into our integral. What is the height of our little approximating rectangle right here? Well, I can find that by using my upper function and subtracting my lower function. The upper function is the square root of x, which I'm going to write as x to the 1/2 power, because it's easier to integrate when I have it in that form, minus 1/2 x, minus 1/2 x, like that. Okay? So that thing is the height. Let's put all of this together now. So my circumference is 2 pi r, but now r looks like 5 minus x. Okay, circumference times height times thickness. My height right here is x to the 1/2 power minus 1/2 x. Like that. And then I have my thickness, which is dx. Okay? I'm going to factor the pi out of here, but I'm not going to factor the 2 out. Normally I would, but I'm seeing that I have this fraction right here, and I kind of prefer to not have a fraction in there if I can help it. I see that this 2 will naturally eliminate that fraction. So what I'm going to do is take this 2, shift it over, and distribute it into the second set of parentheses, which is going to leave me with 5 minus x times 2 x to the 1/2 power minus x dx. I kind of just prefer the way that that looks. So let's take this a step further. In order to integrate this, I'm going to want to multiply this whole thing out. So 5 times 2x to the 1/2 power is 10x to the 1/2. And then I'm going to have negative x times that, which gives me negative 2x to the 3/2 power. And then I'm going to have 5 times negative x, that's minus 5x. And negative x times negative x is plus x squared dx. All right, that is much easier to integrate. So let's do that. Here, I'm going to add 1 to my exponent, which means I multiply by the reciprocal here. I'm going to multiply that by 2/3, which is going to give me 20/3 x to the 3/2 power, minus this is going to become a 5/2, so I multiply by 2/5, giving me 4/5 x to the 5/2 power, minus 5/2 x squared plus x cubed over 3 from 0 to 4. And I realized I actually forgot to work this one out ahead of time too. I am not doing too well on my preliminary notes, it looks like, but that's okay. We'll work this out together. Luckily, we have a 0 as one of our limits of integration, which makes the whole thing go to 0. And that's very convenient because I really just need to plug a 4 into this. Okay, so let's do that. 4 to the 3/2 power. You can actually work that out in your head. Remember, when you have that 2 in the denominator, that's telling you to take the square root of this. The square root of 4 is 2, and then I cube that which gives me an 8. Okay, so now it's 8 times 20/3, which is 160/3. Same thing here. Square root of 4 is 2, and 2 to the 5th power is 32. And then I'm going to multiply that by that 4 right there. 32 times 4 is 128, so I get a minus 128/5. And then what about here? 4 squared is equal to 16, but if I divide it by that 2, that's going to give me an 8, times that 5 gives me minus 40. And then here, 4 to the 3rd power is 64. 64/3, okay? Let's see. I have common denominators already between these two terms. So if I did 160 plus 64, what is that? That's going to give me, let's do that off to the side, 160 plus 64 thirds is equal to 224 thirds. Is that right? Yeah, 224 thirds. And then I would need a common denominator here. So that means I would be multiplying this by 5. And I'll tell you what I'm going to do. Because I didn't work this out ahead of time, I'm going to fill this in my notes, but I don't really want to use the last couple of minutes of this video to do all this arithmetic, especially when I feel like I am likely to make a mistake somewhere. So I'm going to write this into my notes after this video so you have it on Canvas. But for now, I'm just going to let you work through the arithmetic, and we'll fill that in later. I really want to get to this last example here. This is an interesting problem because we're given a region, but we're not given any functions that tell us what this region is bounded by. Instead, it says we have this region below, and we want to rotate it about the y-axis to form a solid of revolution. And we're going to use the midpoint rule with n equals 5 to approximate the volume of that solid. Okay, so here is the axis of rotation. It's the y-axis. Now, if you remember what the midpoint rule is, you take the interval that you would be integrating over, and you break it up into subintervals, and you do a rectangular approximation method with that, right? But the key thing with the midpoint rule is we use the midpoint of those subintervals to determine the height of our rectangles, okay? So because we're dividing this thing into 5 subrectangles, that's what n equals 5 is telling us. And because my original interval that I can see bounding this region over the x-axis, it goes from 0 to 10. If I were to divide that up into 5 equal parts, that would mean I'm looking at subintervals with widths of 2. So 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, and so on. Okay? I want to use the midpoint of each one of those rectangles to give me, or subintervals rather, to give me these rectangles right here. Okay, so notice it's the midpoint. It's one of that subinterval that I'm using to determine this bottom and top to this rectangle. Using 3, I can see that the midpoint would take me here and here. So I'm literally going to draw these in. Here's where my next midpoint is. 5 takes me to here on the lower part of that curve, here to the upper part. I'm constructs that rectangle right there. Here I can see that the bottom and top are here and here, so I'm going to draw this rectangle in like that, and then 9 goes here and here, so I'm going to have this, okay? Now, if all I was looking for was the area of this region, then my approximation using the midpoint rule would just be the sum of the areas of these rectangles. But that's not what we're doing. We're not just looking for the area of that region. I want the volume of the solid obtained by rotating this region about the y-axis. And for that purpose, we're going to think of each one of these rectangles as being rotated around the y-axis to produce one of those cylindrical shells. And what I want to do is add the volume of each of these 5 shells to get my approximation. Okay, so the key thing to remember here is that the volume of a cylindrical shell is circumference times the height times the thickness. Now, the thickness of each one of these shells is going to be the same. It's all going to be 2, because the thickness is determined by the width of each one of these subintervals, each of which is 2. So I know that I'm going to be adding 5 volumes together, but in each one of those, there's going to be a factor of 2, which can be factored out. Okay? So that 2 right there represents the thickness. Now, what's left to compute the volume of each one of these cylindrical shells? It's the circumference times the height. Okay? Well, the circumference is equal to 2 pi r. And that 2 pi is another common factor that's going to show up in each one of those terms. Let's just factor that out as well. If I factor the 2 pi out from the circumference part of this computation, all that's left is the radius. The radius will be different for each one of these shells here, but the radius is going to be equal to the midpoint. For example, when I rotate this first rectangle about the y-axis, 1 is the midpoint of that subinterval, and that's the thing that I think of as my radius when I rotate that about the y-axis. So I'm going to use the midpoint as one of the things that's going to show up in each product that I write in this larger set of parentheses right here. Then I need to multiply that by the height, the only other thing that I haven't determined yet. And I can find the height of each one of these rectangles by just kind of counting the squares in this grid here to determine what it is. So for example, this 2 is the thickness, this 2 pi is part of the circumference, times 1, that's the radius, and then multiply by the height of this rectangle. Well, counting the squares in there, 1, 2. The height of that rectangle is just 2, okay? Same thing for my next rectangle. The midpoint of that subinterval is 3. That's what is representing the radius here. Height of that rectangle is 1, 2, 3, 4. Plus the midpoint, which is 5, times the height of this rectangle, which I can see is 3. Plus the midpoint here, which is 7, times the height of this rectangle, that's 2, plus the midpoint here, which is 9, times the height of that rectangle, which is, sorry, not 18, I was doing the multiplication ahead of time, it's 2. Okay, so now this is a lot of arithmetic, and thankfully, here's one that I actually did work out ahead of time. If you work all of this out, it comes out to 244 pi. Again, don't plug the pi into a calculator, leave it the way that it looks. This is a decent approximation to the volume of revolution that we get from taking this blue region and revolving it about the y-axis. Okay, that's our last example, so we're done with 6.3.